What is the creep? Creep is time-dependent deformation of a material and it typically occurs at high temperatures and under constant stress. These stresses are usually lower than the yield stress. Therefore, we can consider three influential factors on creep: time, temperature, and stress level. Since many industrial components operate under constant stress lower than the yield stress and in high temperature environments, numerous industrial components experience failure due to creep phenomenon. Therefore, the investigation and simulation of the creep phenomenon are of great importance. Among these mentioned factors, temperature has a significant impact on the creep behavior of components. For this reason, it is better to examine the influence of this parameter. The first temperature effect is vacancy concentration. In crystalline materials, some atoms are missing from their intended position in the lattice. These effects in the crystal lattice are called vacancy concentration. Increasing temperature leads to an increase in the concentration of vacancies, and an increased concentration of vacancies aids the creep process. The second effect is thermal expansion. As you can see in the figure, many materials are composed of different constituents, and impurities are also present in materials. These constituents have different thermal expansion coefficients. So it means they do not expand to the same extent when the temperature increases. This leads to the formation of cracks around the impurities. These cracks contribute to the creep of the component. The next effect is grain size. On a microscale, materials are typically composed of internal structures called grains, and the boundaries between these grains are called grain boundaries. The grain size greatly affects the mechanical behavior of materials. Smaller grain sizes result in higher material strength, while larger grain sizes lead to decreased material strength. But how does an increase in temperature contribute to the creep? Due to increase in temperature, grain boundaries are weakened, so grains can slide on each other. This phenomenon helps increase the grain size, which reduces the material strength. As a result, the creep occurs more rapidly. In addition to the phenomena mentioned earlier, increasing temperature also affects other phenomena such as dislocation-related phenomena and phase-related phenomena, which affect material creep. The explanations of these phenomena are beyond the scope of this package, but you can explore them if you are interested. Now we want to examine the creep curve. This helps us to have a better understanding of the stages of creep. Usually, the strain time diagram is used to study the creep process. To examine this diagram, it is better to first review the standard creep test methods. The standard creep test is generally performed in two ways: constant load and constant stress. In the first method, only a constant load is applied to the sample and the amount of load does not change over time. In the second method, which requires advanced equipment, a constant stress is applied. In this method, considering that the cross-sectional area of the sample is constantly decreasing during the test, the force must also decrease in order to keep the stress constant. First, we examine the strain time diagram of constant load method. As you can see in the figure, we need an appropriate model to predict creep behavior. Numerous models have been developed so far for the creep prediction, so we intend to examine some of these models. The Abaqus software provides us with a default set of creep models. We will investigate these models. However, you can also utilize your own customized creep model using the creep subroutine, which will be discussed. The first model is time-hardening law. When dealing with loading conditions where the stress or temperature is changing, it is necessary to have a proper hardening relation to accurately model the material behavior. However, in general, it is not recommended to use the time-hardening relation when the stress is changing. One of the reasons for using this law is its simplicity. It requires fewer parameters for modeling. Equation 5 should be used for creep modeling using this law. In this equation, epsilon dot represents the strain rate. T is time. Q is the Hill's equivalent deviatoric stress for anisotropic behavior, and it is the Mises stress for isotropic behavior. A, N, and M are temperature-dependent constants. According to equation 5, it is better to use this relation for low stress levels. Additionally, the values of A and N must be positive, and M should be greater than -1 and less than or equal to 0. Since stress values are usually large, A should be a very small number. The small value of A can lead to computational issues such as rounding errors during calculations. Sometimes this problem can be resolved by using an appropriate unit system. Another approach to tackle this issue is to use another law called the time power law. Well, now in this workshop we want to simulate the creep process in the Abaqus software. To do this, let me finish explaining the procedure of the simulation. First, we need to create our part in the part module. In the left side, you can see the specimen and its dimensions. Please note that, as we mentioned earlier, we use the US system to avoid computational errors. Therefore, all dimensions are based on inch. As for material properties, we need the elastic, plastic, and creep properties of the material. In this workshop, we will use the strain hardening model for creep modeling. The specimen is subjected to a 1000 psi for 12 hours, and then we examine its creep behavior. Now let's proceed to. Here you can see the specimen after creep. Let's display the specimen in the complete form. We can also remove meshes. In this section, you can choose the desired output parameter for visualization, such as equivalent creep strain or displacements. Other parameters are also available for show. Additionally, you can observe the deformation progress of the specimen. On the other hand, you can see the data such as the equivalent creep strain in form of graphs at a specific point of the specimen. Here you can see the strain time graph. With this method, we were able to simulate the creep process using the Abaqus default creep. Well, in this workshop, we will simulate the creep behavior of a standard specimen. Please note that we will be using the materials from the previous workshop and there will be no changes in the loading conditions. The goal of this workshop is to utilize the creep subroutine. Instead of using default Abaqus models, we will employ a subroutine for modeling creep. To validate the simulation results using the subroutine, we will utilize a strain hardening creep model and compare the results with the previous workshop's simulation. It's important to note that for the creep subroutine, we will use these strain hardening equations stated in the Abaqus documentation to obtain the creep strain rate. This equation is another form of the equation previously used for the strain hardening model. Before starting the simulation in the software, let's see how the creep subroutine operates.